Halle Blend, and I'm here at the Crow Science Building at the Hockaday School looking at Foucault's pendulum. When standing here, it looks like the pendulum is swinging around the pit, when in reality, it's swinging in the same place. This is due to the Earth's rotation under the pendulum, which creates this illusion. How do we think the pendulum moves around the Earth's rotation? Maybe think about it at the North Pole, the South Pole, the equator. I'll give you a second to think about that. At the North Pole, it moves clockwise. At the South Pole, counterclockwise. At the equator, no movement at all. Therefore, we can conclude that as you get closer to the equator, the rate of oscillation slows down. How many times do you think it's knocked over per hour? Well, let's see. If we estimate, there's 4/4 of the whole circle. There's about, we'll say, 45 per section. Therefore, there's about 180 tiles in the whole circle. So if there's 180 tiles in 24 hours, approximately 7.5 are knocked over an hour. If you think about this in degrees, there's 360 degrees in a circle. In 24 hours, that's about 15 degrees of rotation per hour. So where else can we find pendulums in the world? Swings, on a playground, clocks. Look, you can find a pendulum anywhere. Here I am on a swing on a playground. The pendulum swings according to the Earth's gravity. The period is how long it takes for the pendulum to get back to its original point, like that. The longer the string on the pendulum, the longer the period. The shorter the length of the pendulum, the shorter the period. Here we are in the fitness center at the Hockaday School, and in our dance studio, we have the Fibonacci spiral, as you can see in the lights on the ceiling, and it's drawn on the ceiling as well. What is the Fibonacci spiral? It forms the golden ratio, or the golden spiral. How do we get the Fibonacci sequence? You take the first two numbers, 0 and 1, add them together to get the third number, 1. Then you'll add 1 and 1 to get 2, and so on. And it'll grow exponentially as you can see in the curve. Where else can we find the Fibonacci sequence? In nature. You can see it in a pine cone, a flower, many places where this sequence occurs naturally. As you can see here, the seeds on the sunflower follow the pattern of the Fibonacci sequence. So here I am in Metzger Plaza at the Hockaday School, and I'm looking at the focal point of the entire space, which consists of a spiral sculpture. About how long do we think the sculpture is? What we can do is we can measure the distance between the top of one section of the spiral and multiply it by the total number of sections. So, using our tape measure, the distance between those 2 points is about 23 inches. If there's about 1, 2, 3, 4, 5 sections of the sculpture, total length of the sculpture is 23 times 5, or about 115 inches. Here I am in Metzger Plaza in front of the Liza Lee Academic Research Center, and we have some louvers. What is the point of louvers? Well, as you can see, they're angled to where it blocks the most sunlight from getting into the building. Doesn't this sound like something else? Maybe solar panels? Solar panels do the opposite. The solar panels are trying to get the most light, as opposed to the louvers, which are trying to get the least light. Fractals are geometric shapes formed by the veins on the leaf. These shapes are repeated over and over again, getting progressively smaller and smaller as you go towards the end of each leaf. Here we have a tree where we can see the fractal design on each leaf. Looking at the repeating pattern on the leaves, mathematics can help us understand and appreciate how things in the natural world are structured.